Dear students, so in this lecture or in this video, we are going to see the second law of thermodynamics and the concept of heat engine, heat pump, and refrigerator. So this is the second topic or second videos based on your introduction to thermal engineering of subject systems in mechanical engineering. So first we will see what is meant by second law of thermodynamics. So a second law of thermodynamics has been enunciated meticulously by Clausius Statement and some Kelvin-Planck statement. Now these are the two statements of second law of thermodynamics. One is Clausius and another one is Kelvin-Planck's. These both statements are basically identical, but it has a slightly different words in these two statements. So each statement is based on irreversible process. So the first law of thermodynamics, it is based on reversible as well as irreversible process, but this second law of thermodynamics, it is only for irreversible process. So the first consideration, first consider transformation of heat between two thermal reservoir, while second considerations is considers transformation between heat and work. So one is based on only the transformation of heat between two thermal reservoir, and second is based on the transformation of heat into work. So we'll see these two statements. So first statement is a Clausius statement. So it is impossible for a self-acting machine. It is impossible for self-acting machine working in cyclic process unaided by any external agencies. So it is impossible to convey heat from body at lower temperature to body at higher temperature. Actually, heat transfer takes place between body at higher temperature to body at lower temperature. But if you have to transfer heat from body at lower temperature to the body at higher temperature, in this case, we require an external agency or external work done. So it is impossible. If there is no external work, it is impossible to construct that self-acting machine, which is transfer their heat from body at lower temperature to body at higher temperature. Or we cannot, in other words, we say that heat, it cannot flow from colder body to hotter body if there is no work input is given to the system. So this is the first statement. That statement is done by a Clausius. So which means the heat cannot flow naturally from lower temperature, body at lower temperature to body at higher temperature, unless we apply some external work to the system. For example, one is refrigerator and another one is heat pump. Now in the refrigerator, we have to cool the temperature. Means we have to cool the temperature, and for that cooling we require external work, that is external electricity supply will be there or work will be there. Based on that, the body from lower temperature, that is from cold to atmospheric, there will be work done. So from lower temperature to higher temperature, there will be a heat flowing will be there, but only when we apply the external work. So this example of this Clausius statement, it is refrigerator and heat pump. So here the desired effect is cooling effect. Here desired effect is heating effect. So in case of heat pump, we have a desired effect of heating. In case of refrigerator, we have a desired effect of cooling. Now we have another statement, that is Kelvin-Planck statement. So it says that it is impossible to construct an engine. It is impossible to construct an engine which, while operating in cyclic process, produces no other effects except to extract heat from single reservoir and do equivalent amount of work. So this is impossible to take heat from one reservoir, and from same heat we can produce the same work. So it is impossible. So for that, the some amount of heat gets rejected again to the reservoir. So that is the one. So although these two statement appears to be different, but they are really equivalent in the sense that it violations of either statement implies a violation of other statement. So which means there is no thermodynamic system that will operate on 100% efficiency. Example, the heat engine. So there is no thermodynamic system which has 100% efficiency. So these are the second law of thermodynamics. It has mainly two statements. One is Clausius statement, which is based on the convey of heat from body at lower temperature to higher temperature. And second is the based on your engine, where when we there is no other effect except there is extract of heat that is equivalent to equal amount of work. So these two statements are there. One is Clausius, another is Kelvin-Planck's. Okay, so now we will have the, based on this we have heat pump, heat engine and refrigeration. Now we will see these three topics one by one. So first one will be the heat engine. So a heat engine, it is a device which is used to produce a maximum work transfer from given positive transfer of heat. So output of this heat engine, it is the work. So this is the output work, and the input, it is nothing but the heat supplied to that engine. Heat supplied to engine. So the measure of this heat engine, it is called as thermal efficiency of the engine. And this thermal efficiency is defined as, it is the ratio of a net work transfer from engine, that is output is work. So this will be the output, and your input is heat energy supplied, that is this is the input. So efficiency is nothing but the output upon input. So we get the thermal efficiency of engine, it is defined as, it is the ratio of net work transfer from engine to the heat transfer to the engine, that is nothing but the heat supplied to the heat engine or engine. So therefore thermal efficiency we can given as, that is from definition, thermal efficiency is equals to net work transfer, that is the W, divided by heat transfer, that is nothing but the heat supplied to that heat engine. So we get thermal efficiency is equals to W, that is the work output upon input. Now input for this engine is Q1. So W upon Q1. Now W is nothing but there are two heat transfer is heat supplied from heat engine, we supply heat and some heat gets rejected from that supply. So that is the Q2. Now, for example, if you see in heat engine, there is a say ice engine. Now we supply the mixture of air and fuel, and because of burning of air and fuel, we get work. That is nothing but we get power. That is nothing but the rotation of your shaft and wheel. And there is exhaust energy. So energy gets also exhausted by means of uh, the exhaust valve and silencer to the again atmosphere or reservoir. So some amount of energy gets supplied, and from that amount of energy there is work output, and some amount of energy is get rejected to the reservoir. Again, it is to the atmosphere. So we get the work is nothing but the how much amount of energy is supplied, Q1 minus amount of energy released, that is Q2. So we get W is equals to Q1 minus Q2, that divided by Q1. So it is 1 minus Q2 upon Q1. So efficiency is always less than 1. That is always less than 100%. Why? Because there is, this is the minus term is there. So because of this, the efficiency of heat engine is always less than 1 or 100%. So where W is called as net work transfer from engine, that is Q1 minus Q2. Q1 is the heat transfer from hot reservoir to the engine, or you can say heat supplied from hot reservoir to the engine. Q2 is amount of heat rejected or heat transfer from engine to the cold reservoir. So this is Q1, Q2 and W. So a thermal efficiency of engine, heat engine, it is always less than unity or 1, or it is less than 100%. So this is the heat engine. So if in exam there is question on heat engine, so we have to draw this diagram of heat engine, then explain what is meant by heat engine, what is meant by thermal efficiency, then mathematically write down this thermal efficiency, and the important note is there, that is thermal efficiency of heat engine is always less than unity. So this is the heat engine. Now we have two terms based on your Clausius statement, that is heat pump and refrigerator. Now if you see, it is opposite to that of heat engine. So in heat engine, the heat supplied from hot reservoir to cold reservoir and we get work. Now here, the heat is supplied from low reservoir, that is body at lower temperature to body at higher temperature. And for that, the input will be the work. So we require input work. You have to supply heat from cold reservoir to hot reservoir. That is body at lower temperature to body at higher temperature. So in both cases, in heat pump also or in refrigerator also, we have to supply the work to the system. Now this is refrigerator and this is heat pump. So we have to supply the work input and output will be your desired effect. Now for example, in heat pump, cold reservoir, that is nothing but your ambient temperature, and hot reservoir, it is nothing but your temperature, that is the heating effect, heat required. Now in this both condition, we have T1 is always less than T2. This is required because hot reservoir having more temperature, cold reservoir having lower temperature. It is either it is in heat engine, heat pump or refrigerator. We require this. So if you see the cold reservoir, it is ambient temperature. Say it is in winter season, we require this heat pump, or it is also called as room heater. So the temperature, it may ranges from the 14, 15 to 25 degrees Celsius. And the room heater, we require a temperature. It is from say 20 to 27 or 28 degrees Celsius. So based on this, we require a room heater. Now this is used in winter condition. Now we have a refrigerator. So refrigerator, we have hot temperature, it is the ambient temperature. That is atmospheric temperature, say 24 degrees Celsius, 22 degrees Celsius, 23 degrees. and we have a temperature of cold reservoir. It is of 4 degrees Celsius, 3 degrees Celsius, 0 degrees Celsius, minus 1, 2, 3, so on. So this temperature is less. So if you see, both having the here heating effect is there. That is, we have to flow the heat from low temperature reservoir to high temperature reservoir. Here again same, we have to transfer the heat from low temperature reservoir to high temperature reservoir. Again, for that both we require a work. Now, if you see, we will see this heat pump first and refrigerator also in comparison. So heat pump, it is a device which operating in cycle maintains body at a temperature higher than the temperature of surrounding or atmosphere. Here we maintain the higher temperature than the ambient temperature or atmospheric temperature. In a refrigerator is a device which is operating in a cycle. It maintains body at temperature which is lower than the surrounding temperature. So here we have to maintain this, that is lower temperature. Here we have to maintain this higher temperature than ambient temperature. Here again than ambient temperature or surrounding temperature. Now the performance parameter for both heat engine as well as the refrigerator, that parameter is called as coefficient of performance. So there is a performance parameter in heat pump cycle that is called as coefficient of performance, which is abbreviated as COP. Similarly, there is a performance parameter in refrigerator cycle also, which is called as coefficient of performance, and it is again denoted by or abbreviated by COP. Now, what is the value? What is the COP? COP, it is nothing but the desired effect upon work input. So output is your, either we have to maintain the temperature higher than the ambient temperature, or you have to maintain the temperature lower than the ambient temperature. So desired effect upon, now input is your work. Here input is work, output is your temperature. So desired effect is heating effect, work input is W. So heating effect is nothing but we have to maintain this temperature, that is hot reservoir T1. So heating effect is Q1. So it is Q1 upon W. In case of refrigerator, we have maintained this temperature. So your effect required is Q2. So it is Q2 upon W. That is cooling effect. It is Q2 upon work input W. So we can say that COP of heat pump, it is nothing but the Q1 upon W is nothing but again Q1 minus Q2. So Q1 upon Q1 minus Q2. Similarly, COP of refrigerator is equals to Q2 upon Q1 minus Q2. So if you see this COP of refrigerator or heat pump, it is always greater than unity, or coefficient of performance is always greater than unity. Efficiency is always less than unity. Here, COP is always greater than unity. Now we will see one short derivation of why this COP of heat engine minus COP of refrigeration is always unity, or we can say we have a proof that COP of heat pump minus COP of refrigerator is equals to 1, or we can say COP of heat pump is equals to 1 plus this term. So 1 plus COP of refrigerator. So we have formally this COP of heat pump is equals to desired effect upon work input. So desired effect is heating effect upon work input. Similarly, for refrigerator, we have desired effect upon work input, that is the cooling effect upon work input. So COP of heat pump is equals to Q1 upon W. So we have to maintain this temperature. Here we have to maintain this temperature. So it is Q1 upon W. Here we have Q2 upon W. So COP of refrigerator. Now we have a left hand term, that is this COP of heat pump minus COP of refrigerator is equals to, now COP of heat pump Q1 upon W, COP of refrigerator Q2 upon W. Now W taken common, so it is Q1 minus Q2. Again, we know that the Q1 minus work done is nothing but the Q1 minus Q2. So we have a W upon W that is equals to 1. So we can say that the COP of heat pump minus COP of refrigerator is equals to 1. Otherwise, we can say COP of heat pump. Now we take this term to this side, so that is becomes plus. So COP of heat pump is equals to 1 plus COP of refrigerator. Okay. So for that, if this derivation is asked, so you have to draw the diagram for again heat pump, refrigerator, and then from this we have to prove why this COP of heat pump minus COP of refrigerator is equals to 1, or why COP of heat pump is equals to 1 plus COP of refrigerator. So this is all about the second law of thermodynamics. Then the two statement of second law of thermodynamics, that is Clausius statement and Kelvin-Planck statement. Then we have seen the heat engine. We have to find out the heat engine efficiency of heat engine. Then heat pump and refrigerator. We have to find out the COP of heat pump and COP of refrigerator. So thank you for watching this video, and please do subscribe to my channel so that we'll get more video regarding this subject or this unit of introduction to thermal engineering. Thank you very much.